if you're struggling to remember the things from before break, you might have out on your desk today during our notes, your buff sheet of notes. So you can kind of like, hey, if it talks about linear combination or talking about a direct angle or a unit vector or something, you can look back at that and see what it means. And you might do that when you're even working on your homework this evening. Homework today and tomorrow is going to be really important because, you know, the math that you do in vectors is not hard math compared to like some problems that we have done in the past. The math work is pretty simple. It's just understanding what the problem could be asking or how you're going to go about solving the problem. So we're going to be applying some of those things that we learned about last week or the week before spring break. And we are going to apply that to more problems. Okay, so our first problem is here. We're going to find a vector with a given magnitude in the same direction as another vector. I'll give you a moment to jot that down. Directions are really important in these examples. It tells you what it wants you to do. You might jot some of that down. Okay, so when I'm reading this problem, how I'm going to approach this problem so that I can figure out what vectors are asking me to do. Okay, because that's a big goal in these three sections of notes. Find a vector v. So I'm thinking at some point I want component form for v, a horizontal component and a vertical component. I'm given a magnitude, so I know that in the end I want that vector to have a magnitude of 15. But I also know that I want it to go in the same direction as u. U is the vector 1, 2. So, you know, like initially when I read that, I'm like, that doesn't really help me out. What I would maybe start with is visualizing vector u. So for me to visualize, I'm going to go ahead and draw a quick sketch of u. U has a horizontal component of 1 and a vertical component of 2. So there's my vector u. I want a vector that goes in the same direction. So it's going to start at the origin and it's going to follow vector u. But I want a vector that has a magnitude of 15. Does u have a magnitude of 15? Definitely not, right? And in fact, we could find the magnitude of u. The magnitude of u is the square root of 1 squared plus 2 squared, which is the square root of 5. So that's much smaller than the magnitude of 15, right? Okay. So I know that my vector v, I'm just kind of like imagining here, there's going to be some vector much longer, okay? But it's going to follow the same direction of u. All right, so now I kind of like have an understanding of what I'm trying to do. There are multiple approaches to this particular problem. Anybody seeing that picture and visualizing it, and you have an idea of what you might do? Turner, are you raising your hand? Or?
I remember one was the square root of 225 is 15, correct? So the big square root of 5, so you think of it as like ratios, like something like that.
Okay. That's a good place to think about. So you're thinking about ratios. Keep thinking about ratios. Just get you anywhere. Nathan?
If it's in the same direction, it's going to end up having the same angles, or the same directional angle. Since you have a hypotenuse and an angle, you can work backwards with true functions.
Yes. And we are going to do that on the next slide. But I'm going to stick with this for right now. Not that we could find the direction angle. I agree. And that would help us after we know what we know on the next slide. But I'm going to think again. Okay, so here's what I might do. U vector direction, but it's not the correct length. So one thing that I know from the week before spring break is I can create a unit vector. And what would be special about my unit vector? It has magnitude of 1. Thank you, right? That's what's special about units in math, is they are 1. Okay? So if I find the unit vector will be in the same direction, but its magnitude won't be square root 5. It'll just be 1. And then how many unit vectors would I need to make a magnitude of 15? 15. So then I'll just multiply my unit vector by 15. So I would, just like Turner did on that homework problem, I would find my unit vector. So to find the unit vector for you, I'm going to take the vector 1, 2 and divide it by its magnitude, square root 5. Divide the horizontal and the vertical component by square root 5. I'm also going to rationalize right here. So that's square root 5 over 5 and 2 square root 5 over 5. So I'm doing 2 steps in one right there. If you don't like it, you write the middle step. 1 over square root 5, 2 over square root 5. And then you rationalize. Now, that's the unit vector. So that has magnitude of 1. And then I just have to multiply by a scalar 15. So I would say 15 times that vector, square root 5 over 5, and 2 square root 5 over 5. And because I did the rationalizing, this is going to work out nicely when I multiply to both components. I'm going to get 3 square root 5, because 15 over 5 is 3. And then 15 over 5 is another 3, but it gets multiplied by 2, so that would be 6 square root 5. And so my new vector v must be 3 square root 5, 6 square root 5. If I think about the slope, vertical over horizontal component, it's going to be 2 over 1, which is the same slope or same direction as u, 2 over 1. And if I were to plug that into Pythagorean theorem and do the magnitude right there, the square root of, it would be 9 times 5 plus 36 times 5, and then the square root of that should be 18, should be square root of 225. So when you said something about ratio, I think, yeah, there was a ratio. I don't know that it's necessarily with 5 and 225, but it's with magnitude.
Yeah, so like I tried to figure it out, and so what I did was 225 over 5, the letter b, so it's times 45, and b is square root of 45. So you take the square root of 45, multiply it by the 1 and the 2, and that gets your like actual number, so it's like 6.7, and 13, which actually would reduce to 3 rounds.
Now, Turner's doing it a different way, and Mason's doing it another way. So it's like, this is the thing about vectors, is there could be multiple ways to do the same problem. I stuck with mine because we haven't yet done the thing that we're going to do next that would help us with Mason's idea. So here we're going to do Mason's idea, but we're going to have a little bit of forethought with it. Okay, so next up, we're going to talk about what we can do if we're given a magnitude and a direction angle. And what do I actually want us to do? I want us to write component form. Okay, so I'm going to give you a minute just to kind of jot this down. Given a magnitude and a direction angle, can you write component form for a vector? The answer is yes. We're going to look at how. And I've got a picture there where I have labeled magnitude of v and theta. So I'm saying, here's what you know. You know the magnitude and you know the direction. Okay, so remember in component form, That's the one with the angled brackets and the comma, and we've got like usually like I called it that Thursday before spring break a V sub 1 and a V sub 2. It was a horizontal component and a vertical component. So imagine on this particular picture, you know, what would the component form actually be representing? Well, our horizontal component, so that would be our V sub 1, and our vertical component, that would be our V sub 2. And what am I creating right there? That good old right triangle. So now the question becomes, can you rewrite the horizontal component V sub 1 in terms of magnitude and theta? So think about V sub 1, magnitude, theta. What trig function would you be working with right here? Cosine, because it's the adjacent side. So we could write out the equation. The cosine of theta is equal to V sub 1 over the magnitude of V. Then could you tell me what the horizontal component of your vector is? Multiply both sides by the magnitude of V. Mason, is this kind of where you were going? Yeah, and so some of us have this knowledge from physics, so it's like our idea is immediately to go there, but then some of us haven't had physics, so we don't have that immediate thought, which is why I wanted to take that other route on the last problem. But now we could use this idea for our previous problem, for sure. Okay, and then what about V sub 2? Then you get to use sine, so you would say the sine of theta is equal to V sub 2 divided by the magnitude of V. So V sub 2 is really just the magnitude of V times the sine of theta. And that means that in component form, those are your horizontal and your vertical components. Every single time. Don't ask a question. The horizontal component will be the magnitude times the cosine of the direction. And the vertical component will be the magnitude times the sine of the direction. Will always be the case. Okay, whether you're in quadrant 2, 3, or 4. Now, in addition to writing the component form, thank you, then you should also be able to write linear combination. And linear combination, if you'll remember, that's one where, like, don't think too hard. You're not really doing any math. You already have horizontal and vertical components, and you're just pairing them up with the standard unit vectors. So my horizontal component, magnitude times cosine theta, is getting multiplied by I. That's my horizontal standard unit vector, 1, 0. And then my vertical component, magnitude times sine theta, is being paired with J, because that's my vertical standard unit vector, 0, 1. Now it's like number 3 on the warm-up, right? Pair it with I and J, remove the angle brackets. Instead of a comma, it's going to be a plus, because that's what linear combination means. Okay, so this is super important. Star, circle, highlight, asterisk this in your notes. Like, you need to know component form in terms of magnitude and direction angle. Okay, definitely. That'll make your life a lot easier. Let's look at how we can then utilize this. Okay. So I'll do this first example with you. We're going to find the component form for a problem such as this, where they simply give me the information that I need. The magnitude of V is equal to 5, and theta is equal to 30 degrees. So if you look back at what we just wrote down, we're given the magnitude and the direction angle, then we have a formula that we can use for component form. To do the component form, I'd start with my horizontal component. That's magnitude times cosine. And then vertical component is magnitude times sine. Now I will say this. If it's an angle from the unit circle, then I would prefer you give me an exact answer. Because you know what the cosine of 30 degrees is. Exactly. You could plug this into a calculator and still get an answer, but it will be rounded. And I'll be kind of lenient if the directions don't say one way or another, but I would prefer an exact answer if possible. So what is the cosine of 30 degrees? Radical 3 over 2. So that means that this first component, or my horizontal component, is 5 square root 3 over 2. And then the sine of 30 is 1/2. So my vertical component is 5/2. And then you're giving me an exact answer. Now, if that gave me an angle like theta was equal to 32, not on the unit circle, so you definitely would just pull out your calculator and do 5 times cosine 32, write down the decimal, 5 times sine 32, write down the decimal. Be done with it. Okay. So if it's from the unit circle, try to use your unit circle knowledge. Now, the next example I'm going to give you to talk about with your group, and I want you to brainstorm ideas on how you could do component form for the next example. I am aware that it's not exactly like letter A. I did that on purpose. So you and your group are going to talk about, like, how could we do this? There's multiple ways to do it, so I'm hoping that among the 7 different groups we have here, we'll come up with a couple of different ways that we could write in component form. Okay. So with your group, jot this down. The magnitude of V is 2. And then we want the direction of V to be negative 2I plus 3J. Okay, so brainstorm with each other. How would you be able to get the component form? Just for the rules out there. Okay, let's come together and see if anybody's got any ideas. You might not have an answer, but some ideas or some thoughts that we're putting out there. What are your groups talking about? Leah, tell us about your group
What I'm
thoughts.
doing is I'm basically doing like the opposite of A. So I'm doing, or kind of, because you're given the, because like now you're trying to find what the degree is, and so like I'm doing 2 cosine theta equals negative 2. Like for the first one. Does that make sense? I don't know if you can do it, but
Well, okay, so you're then saying, like, you're thinking about these as your horizontal and your vertical components, right? So I'm just gonna, if you don't mind, I'm just gonna write this in component form right there. Now, as you look at that, you want it to go in the same direction of that vector. Does that vector have the magnitude that you want? No. So you don't really want to set 2 cosine theta equal to -2 because that's not going to give you because it doesn't necessarily, v sub 1 isn't -2. Otherwise, we could just write it in component form, and there's component form, right? Okay. So, but I like this idea. Let's go with this, with what Leah's thinking about. She's comparing it to letter A, where you had magnitude and direction angle, and she's disturbed because there is no angle, right? A little bit disturbed, yeah. Where is that darn angle? I've got to find it. So, if you know the linear combination or the component form, can you find the angle?
Yeah.
How do you find the angle? How did we find the angle in the warm-up? Inverse tangent. Theta is equal to the inverse tangent of the vertical over the horizontal component. And when I do the angle there, I get negative 56.3 degrees. Okay, now obviously I know something's up, right? Because it needs to be between 0 and 360. So you might think about this vector, negative 2, 3. That negative 56.3, that must be this angle right here. It's 56.03 or 56.3. So to get the actual angle on the other side, I would subtract that from 180. So then I could add 180, which gets me to 123.7. Okay. And that works. That's an angle in the second quadrant, isn't it? So now we've found Leah's angle. Everything feels a little bit better. Could you write component form? Yeah. So you would do something like the magnitude 2 times the cosine of 123.7 and the magnitude 2 times the sine of 123.7. And those are not angles on the unit circle of 123.7. So I would definitely, I'll find my little X. I would definitely use my calculator here. So I get something like negative 1.110 and 1.664. So that's an example. It's okay to round. It's okay to use your calculator and get non-exact answers in these cases. Okay, so that's one method. If you're really bothered by the fact that you need a magnitude and an angle to use that piece that we just looked at, then find the angle because we have that knowledge from before spring break. Did any groups take a different route or you were brainstorming possibly something else? I'll say this, the other option, have we done a problem recently where we were given the magnitude and we were told what direction we wanted the vector to go in? Yeah, it was 2 problems ago. Okay, so I'm going to just flip back. That was before we had that knowledge about magnitude times cosine and magnitude times sine, and I said, Mason, hold on for 1 second and we'll get there, right? But before that, if you knew a magnitude and you knew the direction of the angle or vector that you wanted to follow, then you could find the magnitude of that vector, scale it back to a unit vector, and multiply by the scalar to get the magnitude that you want. So I could have, on this example, found the magnitude of this vector, square root of 4 plus 9 is the square root of 13. The unit vector will be negative 2 square root 13 over 13 and 3 square root 13 over 13. And then I wanted to have a magnitude of 2, so I would multiply it by 2. And what I would end up with would be negative 4 square root 13 over 13 and 6 square root 13 over 13, which if you were to plug these into your calculator, would equal these decimals that we have over there. So like that's just an either or. If you like this method, if you're like Leah, you were disturbed that there was no angle, then you would find the direction angle and use the trig. If you thought about scaling it back to a unit vector and then multiplying by a scalar to get the desired magnitude, you do that too. Any questions about that? Okay, I'm going to skip the next example because I want to get to one word problem. But I just want to show you this real quick and talk about it because you'll see problems like this on your homework. Find the component form for the sum of u and v. So notice you get magnitude and angle for u. You get magnitude and angle for v. So you can do a component form for u, a component form for v, and then you want the component form that is the sum. So then you just add them together. Okay, so sometimes you have to do multiple component forms and then add or subtract whatever the directions may say. Okay, so that would just be doing extra component form work. This example I want to show you just so you kind of know what to do when you're reading a word problem. Okay, so here we've got a water balloon being launched. It has an initial velocity of 40 meters per second, and it's launched at an angle of 60 degrees above the horizontal. Okay, so horizontal, that's an easy one to draw, right? Water balloon, 60 degrees. And then what you need to know in order to do your homework is that the initial velocity is your magnitude. So 40 meters per second. Okay, so when you're labeling your drawing, an initial velocity of some kind of projectile, that's going to represent your magnitude of your vector. Yeah.
Physics classes.
What's that?
Physics classes. I know.
But you did this in first semester, right? Yeah, but this is the second time you're seeing it, so it'll be a little bit easier. It's great. Sorry if you're seeing it for the first time. Okay? Now, what does the problem want you to do? Find the vertical and horizontal components. So essentially, component form. I would do something like 40 times cosine of 60 and 40 times sine of 60. The one on the left here, that's going to be my horizontal component. This is going to be my vertical component. So 40 times square root 3 over 2 and 40 times 1/2. I will say that these things should be labeled. So you got a horizontal and a vertical component. My horizontal is going to be 20 square root 3 meters per second. And then my vertical is just going to be 20 meters per second. It shares the same label as the magnitude or the initial velocity. So it's like you have initial velocity of the projectile going in the direction of the vector, but now we're splitting it up because tomorrow we're going to do some work and force problems. Okay, so we need to know what component we actually want.